Hello, all of you. Today's topic is op-amp as an integrator. An op-amp can be configured to perform calculus operations like differentiation and integration. In an integrator circuit, output is nothing but the integration of input voltage with respect to time. Op-amp differentiating and integrating circuits are inverting amplifiers with appropriately placed capacitors and resistors. Integrator circuits are usually designed to produce a triangular waveform at the output from a square waveform at the input. An op-amp integrator circuit produces an output voltage which is proportional to the area, that is amplitude multiplied by time, contained under the waveform. An ideal op-amp uses only two components as capacitor and resistors. Capacitor CF connected between an op-amp inverting terminal and an output as shown in figure. Here you can see in this diagram input voltage Vin is applied to an inverting terminal of op-amp through an input resistance R1 or Rin we can say. The capacitor Cf is connected in the feedback path between output and input. The X point is nothing but a virtual ground point. The Vout line for output voltage is shown. Y point is also at ground through a resistor and it is located at positive or non-inverting input terminal of op-amp. Please draw this diagram for your reference further as we are going to derivate an integrator output equation. So, the capacitor Cf is connected as feedback capacitor, so the name Cf, and it is at negative terminal. This ensures that node X is held at ground potential as we said, that is at virtual ground. We all know the capacitor works on charging and discharging process. If input voltage is 0 volt, then there will not be any current flowing through R1 resistor and hence the capacitor CF remains uncharged. The charging of capacitor is not possible. Therefore, ideally output voltage is 0. Again, if a constant DC voltage is given to input of an integrator circuit, that is Vin, then output voltage will fall negative at a linear rate to keep an inverting input terminal at ground potential because this is an inverting op-amp. On the other hand, if a constant negative voltage is applied at input, then output rises linearly, that is, output voltage is positive. The rate of change of output voltage is proportional to the value of applied input voltage. Now, from a circuit diagram, node Y is connected to ground through a resistor R1 and node X is at virtual ground. Therefore, these both points or voltages or potential are equal. So we can say Vx is equal to Vy is equal to 0 because they are ground. One is connected to ground and other is virtual ground. So Vx is equal to Vi equal to 0. We know ideally input current to an op-amp is ideally 0. So current flowing through input resistor due to Vin also flows through the capacitor Cf. Please refer the diagram so that you can understand what is going on. Ideally input current to an op-amp is 0. So current flowing through input resistor Rin or R1 due to Vin, due to input voltage, also flows through the capacitor Cf. So current flows from V in through resistor R1 to the capacitor CF. Now from input side, the current I can be given as I is equal to V in minus Vx, input voltage minus the potential or voltage at x point, that is Vx, divided by R1. As I is equal to V upon R, the input side current is given by the equation I is given is equal to V in minus Vx divided by R1. Here Vx is already, we have said, 0. Therefore I is equal to V in minus R1. This is the equation number 1. Again from the output side, the current I is given as I is equal to Cf into dVx minus dVout divided by dt is equal to minus Cf into dVout divided by dt, as Vx is equal to 0 again. This is nothing but the changes in voltage. D divided by dt is the change in voltage. I is equal to Cf into d dt of Vx minus Vout is equal to minus Cf d Vout divided by dt. Equating the above two equations 1 and 2 of current, we get V in upon R1 is equal to minus Cf into dV out by dt. This is equation number 3. We have equated RHS of both current equations, input and output current equations. Now integrating both sides of equation 3, we get integral of V in divided by R1 into dt is equal to minus Cf integral of dV out divided by dt into dt, limits from 0 to t. Therefore, we get integral of V in upon R1 dt from 0 to t is equal to minus Cf into V out. Therefore, V out will become minus 1 upon R1 Cf into integral of V in into dt 0 to t. In this equation, V out is equal to 1 upon R1 Cf times the integral of the input voltage. What? V out is equal to 1 upon R1 Cf times the integral of input voltage, integral of Vn. Negative sign is just because it is a inverting op amp, where the term R1Cf is known as the time constant of the integrator. The negative sign indicates the phase shift of 180 degree between input and output, we know. Because the input is provided to the inverting terminal of op amp, this is known as an active integrator because op amp is invert, and its main advantage is large time constant, which results in the accurate integration of input signal, that is at the output we can get an accurate integration of applied input. These are the waveforms of integrator. A square waveform is input and its integration at output gives triangular signal waveform. Similarly, integrational sign is a cosine wave, as in trigonometry. You can draw these diagrams of input-output waveforms. Now, what are the applications of op-amp as an integrator? Why should we use op-amp as an integrator? Op-amp integrating amplifiers are used to perform calculus operations in analog computers, most commonly used in analog to digital converters, ramp generators, and also in wave shaping circuits. Okay, so this is all about an integrator circuit using an op-amp. This is very small and easy to understand the working of this integrator circuit using op-amp. If there are any doubts, please feel free to ask in comment section. Otherwise, the topic is completed, that op-amp as an integrator circuit. Thank you.